Hello, I welcome you all in this presentation related with the subject material processing fundamentals and practical. And we are talking about the metal casting. In this particular presentation, I will be talking about the quality of casting and the various ways by which we can examine the quality of the casting. So, as far as the content of this presentation is concerned, quality of casting can be examined in terms of the dimensional accuracy of the casting, whether the desired tolerance is being achieved or not, or the surface finish, the kind of RA, surface roughness, which is being realized on the as cast surface condition, and that will determine whether we need a post processing in form of the machining or not. Then the soundness of casting, like whether the casting is free from the defects or not. If there are defects, then what is the maximum allowed size of the defect or maximum size of the defect which is there. So, because the defect will significantly governing the load carrying capacity, corrosion and mechanical performance of the castings. Okay. The casting quality is also judged from the mechanical performance or properties like the hardness as per the application, the tensile properties in terms of the yield strength, ultimate strength and ductility, toughness, fatigue resistance, etc. So, there are many mechanical properties which can be of the interest as per the application. Then compositional homogeneity, that is another important thing, because the kind of the microstructure and mechanical property that is realized in casting heavily depends on the composition, and if the when composition in turn affects the microstructure of the casting, which in turn affects the properties of the casting. So, but what happens due to the kind of the segregation tendency, okay, during the casting, lot of chemical heterogeneity is observed, and because of this chemical heterogeneity in form of segregation, what we find like the lot of structural variation, which in turn affect the properties. So, the properties that are affected due to the chemical heterogeneity is like mechanical properties and the corrosion properties, okay, corrosion resistance. Then we will also try to see since the cooling conditions which are experienced by the casting during the solidification and after the solidification as well. So, because of the difference in the cooling rate which is experienced at the at the center of the casting and at the surface. So, the cooling rate in these two zones is significantly different, say this is center and this is the surface. So, because of large difference in the cooling rate experienced in these two zones for a given composition of the casting, we find that there is a great difference in terms of the structural features, okay, which may be in terms of the grain size, shape and the phases which are formed, and these two things significantly govern the mechanical and corrosion performance of the castings. So, therefore, it is very important to have the structural homogeneity as much as possible. Okay. So, now we will see the things a little in detail, the dimensional accuracy and surface finish. Like let us say this is the mold and we have taken a metal in the molten form and it is allowed to solidify. So, the different metals, once this has solidified, so the different metals will be shrinking in different ways after the solidification. So what happens, the solid state shrinkage, okay, solid state shrinkage, that depends on the thermal expansion coefficient of the metal. If the thermal expansion coefficient of the metal is very high and the section thickness is also different in the different zones, then what happens, we find lot of variation in terms of the dimensional control, or the dimension, or can say the dimensional control becomes difficult and we find a lot of dimensional inaccuracies. Okay. So, this is one of the aspect, like if the metal is having the great difference, a great or very high value of the thermal expansion coefficient coupled with the large variation in the section thicknesses in different zones, then it becomes difficult to control the dimensions and control the tolerance. Okay. And another factor is like the metal A, when it is exposed to the atmospheric conditions, at a high temperature during the casting. So, you see these atmospheric gases may interact with the metal at a high temperature. So, this interaction can lead to the formation of the oxides, nitrides at the surface, and that can result in the rougher surfaces. Okay. So, but this will depend on the affinity of the metal with the atmospheric gases. So, if the metal is having the greater affinity with the atmospheric gases, then the chances of the interaction between the metal and the atmospheric gases will be more, and that will increase the tendency of the getting more roughness. Okay. Apart from these the metal related aspects, the casting process significantly affect the dimensional accuracy. Why? Because let us say that will depend on the like sand mold casting. If we talk about sand mold casting, so here our casting will be made using the sand mold, which is prepared with the help of pattern. Okay. So, here what is important, like the pattern can experience multiple changes in the size and shape due to the abrasion, absorption of moisture or interaction with the molding sand. So, if the pattern changes the size and shape due to the multiple factors associated with the pattern, then pattern will be resulting in the mold which is of not desired size and shape, and that mold in turn will be resulting in the casting which is also of the not the desired size and shape. So, it will depend heavily on the dimensional accuracy of the product being made by the sand mold casting will depend on the kind of the pattern, especially this is true in case of the wooden patterns, which will have the greater tendency for the change in size and shape. So, it is very important that the dimensional accuracy, size and shape, morphology of the pattern is also checked regularly to ensure that whatever mold is prepared, that is as per the need to produce the castings of the desired dimensions. Okay. In die casting, you see we use the metallic dies. Okay. So, the dies will not be experiencing much of the change in dimensions, whatever the change that will be happening due to the thermal expansion only, thermal expansion of the die. So, that can cause the minor change in the dimensions of the mold, and so the dimensions of the casting. Likewise, in the case of the investment casting, it will depend upon how accurate the pattern of the wax is prepared to be creating the ceramic shell mold, okay, for the investment casting, and that in turn will govern the dimensional accuracy. But as far as the roughness is concerned, in case of the sand mold, the roughness sand mold casting finish depends on the size of the sand particles and the size range. No, if we use large or coarse sand particles, then the roughness of the surface that will be realized, that will be more. Why? Because the coarse sand particles will be offering the little rougher surfaces of the mold, and that in turn will be producing the rougher surfaces of the casting. And similarly, if we are using very wide range of the sand particles of the different sizes, then the wide range sand particles will be filling all these gaps. This will be allowing the smoother surfaces of the mold. Okay. So, the greater the size range of the sand particles, then smoother the mold surface will be realized, and that in turn will be helping to produce the smoother casting. Okay. Then as far as the die casting is concerned, the roughness of the casting will depend upon the roughness or A of the die, okay, or you can say the metallic mold which has been prepared. Okay. So, how good the surface finish of the metallic mold is, that will determine the roughness of the casting. Similarly, in case of the investment casting, we are using the ceramic powder particles for making the shell mold, okay, in investment casting. So, the particle size will determine the roughness of the internal surfaces of the shell mold, and that in turn will determine the roughness of the casting itself. Okay. So, how to measure this roughness and the finish, surface finish and dimensional accuracy of the casting. Initially what we do, we try to examine the casting visually, and then we use the metrological equipments. Metrological equipments and the tools help in establishing the dimensions and the variation in dimensions. So, that is done with the help of suitable comparators. So, comparators will allow us to check how close the component is with respect to the desired one. On the other hand, the roughness is checked using the roughness testers. Okay. So, the roughness testers are of the broadly two types. One is the contact type, where typical stylus probe runs over the surface to examine the surface of the surface roughness, and other is the non-contact type. Okay. In non-contact type roughness testers. So, they both will be giving us the roughness, the in most standard, in terms of the most common the parameter of measuring the surface roughness, that is A, center line average value of the surface roughness, that is represented using this A. So, the suitable methods can be used to establish the surface roughness, but these are the various factors associated with the surface dimensional accuracy and the surface finish. Now, as far as the soundness of the casting is concerned, means how good or free from the defect casting, defect free casting is. Okay. Sound casting means how free or freedom from the defects. Okay. So, this will depend upon what, like certainly it will depend upon the this. So, this soundness, if the defects are significant of very large size in form of porosity, blowhole, cracks at the surface, then certainly the casting will be rejected because of the reduced soundness of the casting. Therefore, soundness is one of the major parameter affecting the quality of the casting. So, soundness of the casting significantly affects the quality of casting, and that in turn depends on the quality of the molten metal. So, there are two main aspects that are affecting the soundness of the casting. One is quality of the molten metal, this is one, and other one is the process specific parameters. Okay. Process specific parameters, say for sand mold casting, for investment casting, for die casting, these parameters will be different. Okay. So, what are the ways by which to check the quality of casting? Quality of the molten metal. Quality of the molten metal is determined by the temperature of the molten metal which is being fed into the mold. Okay. Usually this is kept little say 50 degrees centigrade above the melting temperature, so that the molten metal is able to fill all the fine gaps also in the mold and to produce the sound casting. This is one. The second is the molten metal must be pure, means it should be free from all kind of the impurities, oxides, dross, sand particles as per the case. So, if the molten metal is free from the impurities, then certainly the casting of the good quality will be produced. Okay. So, here what we can see, the quality of the molten metal is one of the parameters apart from the process specific parameters that will be governing the quality of casting or the soundness of casting. So, as far as the quality of the molten metal is concerned, there are two aspects. One is the temperature and another is the purity of the molten metal, because these affect the tendency of the defect formation and cracking tendency in the molten metal in the casting. Okay. The molten metal must be fed with enough degree of superheat, say 50 to 100 degrees centigrade above the temperature or melting temperature of the metal, so that there is a sufficient fluidity associated with the metal and sufficient time to fill the mold cavity before the commencement of the solidification. So, the superheat must be enough, superheat of the melt which is being fed must be enough, say 50 to 100 degrees centigrade. So, when this is done, then it takes enough time, it provides enough time for filling the different zones. Okay. So, time to fill the mold cavity before the commencement of the solidification, and it also helps in improving the fluidity. Okay. So, better fluidity at a higher temperature due to the lower viscosity, lower surface tension facilitates the easier filling and faster filling of the molten metal in the finer zones of the mold. Okay. So, it is important that the temperature of the molten metal is maintained and controlled properly. Okay. This is one that is important in governing the quality of casting. Say if the temperature is low, what will happen? This will increase the surface tension, increase the viscosity, that will reduce the fluidity, and what will happen? It will take very long time for filling the mold, and there is a very much possibility that few unfilled section will be left. That is one. And the second one, the solidification will start even when the mold has not been filled in completely. So, that in turn will be leading to the presence of multiple defects. Okay. So, here in general, reduction in melted temperature increases the viscosity and surface tension of the molten metal, which in turn decreases the fluidity. Reduced fluidity means increased requirement of the long time for filling. Okay. This is one, and we may not have that much time. Okay. The second aspect is, if the molten metal has become viscous, then it will not be able to get into the finer sections of the mold. So, that will be leading to the incompletely filled mold, okay, and leading to the formation of the or development of the casting, which is not really of the desired shape. Okay. Reduction in fluidity causes the longer time requirement for filling the mold cavity, which in turn increases the chances of casting defects like cold shut and mishran. Mishran is due to the unfilled section, and the cold shut is when the low temperature molten metal streams coming from one side does not mix well with the stream coming from another side, and that leaves an interface between the two. This kind of the defect is known as cold shut, and this happens particularly due to the low temperature of the molten metal. Okay. So, these are the two kind of the issues which are commonly encountered due to the low temperature of the molten metal. Another is production cycle time is increased, because it will be taking longer time to fill the mold cavity, and that in turn will increase the production cycle time, and increased production cycle time basically be affecting the productivity adversely. So, productivity is reduced. Okay. So that was one of the aspects related to the melted temperature. Another aspect related to the melt temperature, molten metal, is the quality of the melt, which is also judged from the purity of the melt. So, the freedom of the melt from the dissolved gases, solid particles, dross and flux. Okay. So, if it is free, then our quality of casting will be really good. Okay. But if it is not, then then certainly there will be the defect formation tendency in form of inclusions, porosity, cracks, etc. Another aspect is the compositional homogeneity. Say it is very much possible, like the molten metal being fed first is of one composition, and which is coming later is of the different composition. So, that will be leading to the chemical heterogeneity. Okay. So, the composition homogeneity of the composition of the melt with the desired alloying element for refinement purpose and for modification purpose to develop the casting of the desired structure and properties. You see, during the casting, what happens, there is a molten metal in the furnace, and if it is held in the furnace for very long time, like say 1 hour, 2 hour, then the segregation or settlement or the flotation of some of the alloying elements start, or even the chemical interactions between the different elements start, and that lead to the formation of the impurities and a lot of variation in the composition in the molten metal, which is being fed first as compared to the one which is being fed in the later stages. Okay. So, because of this, what happens, we do not find the desired refinement, desired composition, desired microstructure, or desired modification in the microstructure, and if that happens because of the compositional heterogeneity, then we will not be having the desired microstructure and mechanical properties. So, compositional homogeneity apart from the freedom from the impurities in the molten metal. This is the another aspect that determines the quality of the molten metal. So, suitable alloying elements and filtration of the molten metal is done to supply the good quality of the casting. So, what we have to do to ensure the quality of casting, like proper melt temperature, okay, then the purity, okay, purity of the melt by removing all impurities, basically impurities are minimized, okay, and then compositional homogeneity is also ensured. Compositional homogeneity is ensured. For if we have these kind of the aspects, then our quality of the molten metal will be good, and that in turn will help in developing the quality castings, okay, which are free from the defects. Why the defects or the what is the importance of the soundness of the casting means, if we have a casting like this, but it is having the porosity and inclusions like this, okay, if there are inclusions and porosity, then what will happen, these are the non-metallic things, okay, or even if there is a crack at the surface. So, what will happen, wherever there is a defect, the defects will do the two things. One, they will reduce the load resisting cross sectional area. Okay. Once the load resisting cross sectional area is reduced, then of course, load carrying capacity of the casting is minimized. Another way is that these defects, wherever these are, they will be increasing the stress concentration. So, stresses will be getting localized when the casting is subjected to the external load. Okay. So, the due to the stress localization or due to the stress concentration and reduction in load resisting cross sectional area, these reduce the load carrying capacity of the casting significantly. Therefore, it is important that the defects in the casting are minimized to improve the performance of the casting. So, the defects reduce the load resisting cross sectional area and increase the stress concentration, and these factors in turn reduce the load carrying capacity or the mechanical performance of the castings. Okay. How to establish if there are defects? So, as far as the establishing the defect is concerned, we have to see what is the size of the defect, okay, and what is the morphology of the defect. Okay. It is the spherical or it is like a elongated needle shape, or where it is present, like it is the surface defect or internal defect. Okay. So, obviously, if we see the small size defects maybe can be tolerated depending upon the criticality of the application. Similarly, the spherical shape defects can be tolerated if as per the criticality of application. So, and the internal defects. So, internal defects. So, if we talk of small size defects of a spherical morphology located inside, these are considered to be the less damaging and harmful, less harmful for the performance of the casting. On the other hand, if we have the large size casting, large size defect, defect size is large, one, and the second, it is present at the surface, and third, it is of the high aspect ratio. High aspect ratio means the length to width is very high. Say in case of cracks like this, so length is this, width is very limited. So, length to width ratio is very high, say 5 or 10, then these will be considered very damaging or harmful for the performance of the casting. Okay. So, what can be done to establish the casting defects? So, what we have to do is, for establishing the surface defects, what we try to do? We try to do the dye penetrant test, okay, and we can also do the magnetic particle testing or eddy current testing. Okay. So, here DPT or dye penetrant test, this is very easy and the simple test, and it can be applied for any kind of the material, but the magnetic particle testing is applicable only for the magnetic materials only, the castings of the magnetic materials. And likewise, this ECT eddy current testing is also applicable good for the electrical conducting materials, electrical conducting materials of the casting only. Okay. So, if we talk of the techniques which are used for establishing the soundness of the casting, of the, if it is having an internal defects, then internal defects are established through the ultrasonic testing or radiographic testing. So, in radiographic testing we have X-ray and the gamma ray test. Okay. So, the good part here is with these tests we are able to establish the record of the test, if there is a defect and what size and shape of the defect is, with the help of the ultrasonic as well as with the radiographic test. So, these tests allow us to not just to find out the size, but also the location where the defect is present, and that also help us to see how harmful the defect can be. So, we can take a call whether the defect has to be accepted or not as per the acceptance criteria for the casting. Say there are defects in a casting, okay, like this, cracks, inclusions, porosity, etc. Okay, at the surface or near surface layers. What we do, there are two approaches which can be used or commonly used. One is, if you can just remove this, if you have enough material, just remove this material so that the defective part is removed. But if that cannot be done, then what we do, we use the controlled heat input, okay, for localized melting up to the desired depth, so that these defects they are removed, like say the cracks or inclusions, porosity, everything gets removed. So, this is called the remelting of surface layers. This can be done using the TIG arc or the laser or any suitable heat source that is available. Another way is this, like using the suitable tool, okay, like for friction stir processing we can use the suitable tool, a tool like this, say this is a shoulder and this is the tool, and if you have the defect near surface layers, then the tool is made to pass through the surface where there is a defect. So, the friction stir processing will just close down and distribute and break all these defects in the very fine size and will neutralize the effect of the defect. Okay. So, that is another one. Hammering and pinning also helps in closing all these defects, if that also can be done. But in those cases, we use the controlled surface layer, the deformation approach of eliminating the defect. Okay. Now, coming to the metallurgical characteristics of the casting, we know that when the molten metal is poured into the mold, okay, heat is dissipated to the mold wall, okay, like this. So, initially the whatever is the molten metal coming in contact with the low temperature mold wall surface, that will be cooled very rapidly. Okay. So, the skin of the casting is cooled very rapidly, and that is why we get very fine grain structure near the surface layers. But as we move towards the center of the casting, what happens, the rate of cooling keeps on decreasing towards the center, and therefore, we find a great change in the structure of the casting right from the surface to the center, especially when no special alloying elements have been added for refining the grain structure. So, the microstructure of any casting depends on the two aspects. One is the composition of the molten metal, and the second is the kind of cooling rate which is experienced by the molten metal during the solidification and after the cooling rate experienced after the solidification of the casting, especially in case of the transformation hardenable metals. Okay. So, if the cooling rate is high, then what we get, in general we get the fine grain structure. Why? Because of the high nucleation rate and the low growth rate. Okay. So, when high nucleation rate and low growth rate is observed due to the high cooling rate, then we find the very fine grain structure. Okay. So, let us talk about the kind of the different kind of the morphologies and the geometrical features of the grains which are found. So, the metallurgical characteristics like the grain structure and the phase structure of casting are primarily governed by the composition and the cooling rate which is experienced by the metal during the casting. Okay. So, in case of the most cast metals, except those which will be experiencing the transformation hardening, like the phase transformation that is observed due to the cooling rate being experienced after the solidification. Okay. So, in that case the initially there will be one phase, then after cooling down to the room temperature. Depending on the cooling rate, we may have the different kind of the phases. So, in most of the cast metals where there is no transformation hardening, a typical cast structure in form of planar, cellular, dendritic and equexed grains is observed of varying grain sizes depending upon the cooling rate and the composition. So, that is what we can see at the surface. We have very fine equexed structure, then we have columnar cellular structure and then the columnar dendritic structure and equexed structure. So, this is what we get: equexed structure at the surface, then the cellular structure, then the dendritic structure and again equexed structure at the center. Okay. The size and the type of the grain structure varies from the surface to the center due to the cooling rates being experienced. This is true for those metals where there is no phase change during the cooling from after the solidification to the room temperature. Rapid cooling of the molten metal at the surface by the mold wall leads to the extremely fine and equexed grain structure, resulting in the higher hardness at the surface as compared to that of the subsurface region and the center. So, this is what the fine equexed grain structure is observed at the surface, and the rate of cooling experienced by the molten metal in the subsurface zone on moving from surface to the center, that will be gradually decreasing, and therefore, we find the different grain structures: equexed, then cellular, then dendritic and then equexed at the center again. Okay. Therefore, heterogeneity in the microstructure of the cast component results in the significant variation in the hardness and the mechanical properties from the surface. Because of the grain structural variation, we find variation in the properties of the casting. A very thin layer of few micrometer of the casting surface experiences very fine equexed grain structure due to the quenching effect of the molten metal with the mold surface. This will be true especially for the metallic molds and the sand mold having the moisture. Okay, sand mold with the moisture. So, if there is a lot of moisture in the sand mold, then the quenching effect will be there, and also in case of the metallic mold, that will be resulting in the very fine equexed grain structure at the surface. Therefore, on approaching the center of the casting, planar, cellular, dendritic and equexed grain structures are observed. What happens in case of the casting of the transformation hardening metals? Say this is the mold and it has molten metal in the beginning, and once it is solidifies, initially it will be forming in case of the transformation hardening metals like cast iron, or in case of the steels. What we have initially, we get the austenite. Austenite, depending upon the cooling rate being experienced in a particular zone, this may lead to the formation of the martensite at the surface, followed by the fine perlite and ferrite, and then coarse perlite and the ferrite, depending upon the cooling rate being experienced in a particular zone of the casting. Okay. So, transformation hardening metals like cast iron and steel undergo solid state transformations after solidification of the casting. Typical cast structure is usually not observed in the castings of the such transformation hardening metals, and a hard surface layer due to the quenching effect is invariably observed in the transformation hardening metals. This is due to the tendency of the formation of the martensite and benite at the surface, while at the center it contains primarily the perlite and the ferrite. So, if we see divide in these two parts, so at the center we will have the ferrite and perlite, while at the surface it will have the martensite and the benite. So, if these phases are there due to the rapid cooling, higher cooling rate at the surface, while the slow cooling at the center. So, we find a lot of variation in the structure and properties. Okay. So, now here I will summarize this presentation. In this presentation, we have talked about the important factors which need to be seen to assess the quality of the casting. These may be in form of the dimensional accuracy, surface finish, the microstructure, mechanical properties and the chemical homogeneity of the casting, apart from the soundness of the casting. Thank you for your attention.